Welcome, everybody. Welcome to our Science Thursday with Brookhaven National Lab. I'm Aleida Perez from the Office of Educational Programs here at Brookhaven, and I'm joined by my colleague, Diana Murphy, who will manage the Q&A portion of the discussion. Before I introduce our guests today, I have a few reminders. Please submit your questions using the Q&A chat section, and we will try to get to as many questions as we can today. If you have any issues or difficulties with the stream, you can let IT know by making a comment in the chat section. Great. So today I am joined by Dr. Stuart Wilkins. He is a physicist and program manager for the Soft X-ray Scattering and Spectroscopy Group at the National Synchrotron Light Source II. Stuart is joining us to talk about quantum materials, science, and its applications. Welcome, Stuart. How are you?
I'm doing good. How are you?
I'm doing great. It's truly a pleasure having you here today.
No
As people may be getting aware in the news and what we hear around, quantum is a word that you are hearing more and more about as a solution to create more powerful computers and reach quantum supremacy that IBM, Google, and others are trying to achieve, and to create more secure internet. And it's driving innovation in a sector that is projected to achieve a revenue at about $13 billion by 2023, which is big. So in addition, the White House Office of Science and Technology Policy and the National Science Foundation and the U.S. Department of Energy recently announced over $1 billion in awards for the establishment of 12 new artificial intelligence and quantum information science, the QIS research institutes nationwide. So to establish the quantum information science research centers, the Department of Energy is awarding $625 million over 5 years to several national laboratories, and those include like Argonne National Lab in Chicago, Fermi in Chicago, Oak Ridge in Tennessee, Lawrence Berkeley in California, and here at Brookhaven as well. So each of these centers will incorporate a collective research team with multiple scientific and engineering disciplines and multiple institutions. So, reaching out to our young folks, our teachers and educators creating awareness for the next generation of the new science that will come out of this endeavor. So Stuart, you are leading one of the areas in the Brookhaven lab QIS centers. Can you tell us a little bit about what quantum is? And a little bit about the science that your group does in looking into the quantum materials and the quantum science.
Sure. So I think I could maybe start by just saying there's kind of, two things here that I think are kind of interesting, right? One of them is, as you mentioned, at Brookhaven, this new QIS center, the Center for Quantum Information Science, which we're calling the Co-Design Center for Quantum Advantage, which is a real collaboration between the national labs and a lot of universities. At the moment. The other thing is that all of my research is at the National Synchrotron Light Source II at Brookhaven, which is, while I have a group of scientists who are working there on this, we're actually a user facility. And so we have users who come in from all over. They could be people that are in universities, it could be other national labs. We have industry that comes into us. And we even have experiments coming from high schools that come and actually do experiments here at the synchrotron source. And while I'm very interested in doing experiments for quantum materials and quantum information science, the facility spans everything from biology and doing work in protein crystallography, all the way up to the physics that we see. So that's really gives you a kind of picture of where I sit here. And I think it's really exciting to be in a place where we get so many different users that are coming in and doing different type of science. But one of the things that's nice at Synchrotron at NSLS-II is we're actually one of the brightest light sources in the world actually at the moment, and that's really good because it lets us see everything about the electrons, right? Everything that's going on in these new quantum materials.
So what is it about the electrons? And you mentioned the electrons, right? What is it about them that makes them so special? Just little pesky negative charge, particles.
Sure. So, I mean, so what's interesting is if you think about most materials, and I think of as a material scientist, solid materials, so they could be things like everything from the silicon technology that's in every computer and we're probably all using at the moment. What defines that material's property is really the electrons and how those electrons interact. You know, in a classical world, right, electrical conduction happens because electrons drift through copper, through cables, and they come out, and that conducts electricity. We have situations where we have, devices such as computers, and a lot of the way we understand how, say, silicon technology works is because we have electrons that interact in a very weak way with each other, and we're not really exploiting their quantum properties. So what quantum's about to me is about using those quantum properties of those pesky negative charge particles you're talking about, where we can actually use things like their spin. And so electron's nice because it can either be up or down when we look at spin. And so we can exploit that property to do some really kind of, neat kind of things. One of the things you can do is if you can get a superposition of those together, right, you can separate out those electrons. And the minute that I know when one is up, I know at the other end it's down. And so you can do this thought experiment where you take one and you leave it in the White House, and one you can take back to Buckingham Palace, and now you've got the fact that you can transfer information at the speed of light, which is something that's really quite exciting to be able to do.
I agree. And so that's you're looking at the different ways that these electrons will come together, right? How you position them into the materials, into the material pieces, and to create this, whatever those materials might be, that has to be new in order to power this quantum computers, for example.
Right. So yeah. So just like in a traditional classical computer, we have a bit, right? A bit of information. And so in the quantum world, we have what's called a qubit, which is a bit of quantum information, or qubit. And so what's nice about qubits is we can use exactly that entanglement, right? And so what we can think about is that you can create two qubits, entangle them together, and they become this superposition together.
So okay. For our folks, and when you talk about entanglement, you're talking about two qubits that are joined together, and when they're joined, they kind of behave the same way, or they do.
And I think the way that we think about it is that we can't describe those qubits at all to be separate. And so this is kind of one of these quantum things where there is just no way we can describe the system unless it's one entity. So those two are locked together, and that it's indistinguishable from each other. Maybe the way to say it.
Stuart, there are two questions that I want to just bring up. So the first question is, are quantum computers' strength performing many simultaneous computations?
So the way I understand it, and I was talking earlier with you, right? I am actually a physicist, and I don't design quantum computers. So I'm actually going back to the knowledge of physics I had, and it's kind of exciting because this is an area I'm learning at the moment. But the way that quantum computers are good is that, yes, they can actually do simultaneous operations. That's one of the things qubits can do. And the way that I think about it is that the quantum computer can do everything a classical computer can do. What quantum supremacy is about is being able to do operations that would take basically huge amount of time that you'd never be able to run a computer for, that a quantum computer can do very quickly. And so they're really applied to certain applications. And one of them that we're very interested in at the moment is actually doing physics simulations to advance that at the moment.
Yeah, and so those simulations that you cannot do otherwise would take a long time, right? So now with this quantum computer allows you to move a bit faster. Before I just want to give you another question that came in, that was in our chat. What sort of additional information do we gain from looking at the X-ray domain as opposed to the traditional optical, infrared, or THZ domains?
And the terahertz. So
yes.
Yeah. So I think, what X-ray diffraction gives you is many different things, right? One of the things is we can see, for instance, how the spins of electrons behave, because we can see magnetism with that. The other thing is we can actually just do quite a lot of material science. what it turns out that one of the problems with qubits is we need to make them well, and being able to see their structure and how they behave, and whether when you have somebody who fabricates a qubit actually makes the right thing is something that X-rays can give. And so, to answer that question, we have a sense of having this large kind of, how should I say, tools to give all the possible measurements to be able to look at it, everything from the structure to looking at some of the properties. And then, yes, we have other lab techniques such as terahertz imaging or infrared that can do that at the moment. I would also add that synchrotrons are actually, although they're X-ray sources, they actually are a very good source of infrared X-rays at the moment. And coming along with the C²QA Center is actually the possibility to build a new infrared beamline from the source.
So just to follow up from that question,
yeah.
Stuart, so when you're using the light source as a tool to understand this electrons, or how they behave, how do you know that the information that the material that you are looking at has the properties that will make it a very good material, let's say, for quantum bits or quantum computers?
So I think there's a couple of things here. So one of them is that, well, I could tell you my dream, which was where we ultimately get to. It would be great to have a working quantum computer in an X-ray beamline so that you. That would be great. That I think is a a long way off at the moment. But what we do is, and this is one of the nice things with the center, right, is we work with people who are doing these measurements in their labs at universities, and they will send us the samples to the synchrotron, and we can do the measurements here. And then this is kind of one of the processes of how science works, right? You find a material that's got a really good property, say the coherence time is very good. We then study it to understand why. And if we understand why, we can then go back with the people who make the samples and tell them, keep making good samples that way. But also at the same time, we understand the physics of how they actually work. And so you gain two bits of knowledge, right? You get a better device, but you also advance physics at the same time by understanding how they operate.
That's very cool. There's a question in the chat. It has to go back to the electron, those little, particles. Which materials, electrons, can be used for quantum computer? Are correlated electron materials particularly good at being used for quantum experiments, computing, as opposed to normal materials?
Yeah, so that's actually a really good question. So quantum correlated electron materials, which I actually should say I did a lot of work on before and are being used now. In fact, my thesis was on correlated electron materials a long time ago. So one of the things that's very promising is to use superconducting qubits. And superconductors are actually, if we can use certain superconductors, we can actually make pretty good qubits out of them. That's a lot of material science that needs to happen at the moment, but there's a real possibility there to use these quantum materials for that.
So when you think about the qubit, that piece that almost like a transistor, transistor, but that's the analog that I can think of. Yeah. What kind of materials they're made of? What is the ideal material that you will start looking for in terms of building this qubit?
So I mentioned before we use superconductors. So we actually have, for instance, materials that are made of niobium in there, and they're actually made in through lithographic techniques. They're actually made into certain structures from that, and so it's about understanding whether that pattern, that structuring is actually made correctly. And so it's not just whether the material is, say, pure or not. And I mean, one of the challenges we have is that, the reason silicon as a technology for doing semiconductors and everything we know about now is so good is that we can get it really pure, right? You can actually make really, really, really pure silicon through techniques that have done, things like zone refining now. Unfortunately, the materials we make qubits from, we don't have that benefit, right? We can't make them that pure. And so that's why I think a lot of research is happening at the moment is understanding how, if the material is impure, how it affects those properties, right? Do we need to do better refinement? Do we need to, do this? And I think that it's a hard question to answer, but I think it's that process that goes on, because what we can't do, which would be great with an experiment, right, is be able to understand how to measure coherence time with the properties, right? That's not a physics experiment we can do. So we're actually trying to piece together many different measurements.
There's one question on the chat. Stuart, it says, how many orders of magnitude greater is a quantum computer in contrast to a supercomputer?
Yeah, I really don't. I'll just share with you. I really don't know how to answer that. I think that you know, there is the perspective that a quantum computer could do certain things like factorization really, really fast. Having not necessarily done that in those circumstances yet, I think we don't know, and I will share with you. I don't know the answer, you know, fully to that.
Mm-hmm. Yeah. So, so going back, I know that your focus is on the material science
Right.
piece and knowing what those materials are that need to be understood, how they
Right.
behave, how do you even manufacture them too,
Right.
in order to make those pieces, in this case, the qubits that are part of this quantum
Right.
computing world that yeah, you're looking that we're looking for. So you use the light source as a user. So how many, how long these experiments tend to take at the light source when you're looking at this material science kind of experiments?
So I think, you know, it a little bit depends on the experiment you're doing. So if you're doing, say, you know, an X-ray diffraction experiment, maybe to look at the structure, the crystalline structure of one of these materials, you know, you can do that in hours. But there are other experiments we do in my group where we're really trying to look at quite exotic properties of the electrons, such as things like looking at how the electrons together can operate in spin waves. And those experiments actually are very challenging to do. We get very low count rates, even though we have a bright source, very low intensity of X-rays, I should say, at the detector, and they can take a week. And so we have everything from people doing an experiment in hours through to a team of people that are doing 24/7 for 5 to 6 days, sitting on a beamline, you know, waiting for the data to come in. So we really have both ends of both extremes there.
So yeah, it's a very exciting place to be. I had the privilege to use the facility with students, and I think it's exciting to be there. And you're right, the type of experiment will change and determines how long or how short your tenure at the light source it might be, or it would be. So when we think about the quantum, the research that your team does together with others, what kind of impact, what kind of long-term impact or applications do you think come out of that kind of research?
So I think, you know, in my mind, I think there's kind of a few things that come out of this. You know, obviously, you know, we've got this stated goal, and I think it's really important to try and build a very good quantum computer eventually, which I think is a huge challenge, really for the nation to be able to do. The other side is that if you think about most of the electronics that we use today, so like, you know, I come back to, you know, if you like pick up, well, Zoom doesn't like it, right? If I do it in front of me, right? Pick up your iPhone. You know, the technology that goes into that at the moment is all silicon-based technology, and it's all back to those weakly interacting electrons we were talking about. And you know, that's based on physics that was 1950s, 1960s that was worked out. And what engineering has done, or the process has done, is really kind of like ran with that technology and scaled it. And so we've gone from transistors, which, you know, when they first started were maybe this size, to now, you know, I think I was watching a webinar by Apple, right? They now have a 5 nanometer process to make silicon. And at some point you hit a limit, because that's a few atoms. And if you get any smaller, you can't make those transistors smaller. The other problem is that with the silicon technologies, it gets hot, right? I mean, I'm talking to you now and the fan's whirring on my laptop doing the video coding, you know, talking. And so what we'd like to do is use quantum materials to kind of break through that. And by using these quantum properties, we can do things like have materials where processors can operate so they use much less heat. We can break through the barriers that we have from silicon. And then if we start using quantum properties in qubits, we can do that. So it's really talking about everything from the next generation electronics through to how computing is going to be done in 50 to 100 years time, maybe even 10 years time. You know,
that is true. So when you talk about silicon, and this might be a silly question to ask, but I'm just wondering. So, by understanding, for example, if you look at silicon, can we give some a material that is well known and understood, perhaps some new properties to this quantum process, or am I wrong in looking at it that way? And it's just simply new materials needs to be understood and made.
I think the silicon wouldn't be a possible use for these things in these kind of materials. We need to look at other elements, if you like, or other materials made from that. You know, silicon was used because of its band structure, partly because it's very, very pure, and people, you know, got it to work.
Got it. So there are a couple of questions that are coming in, and I will share a few of them with you here. So one question that I asked is that in the chat is, will quantum be a viable replacement or use for consumer electronics?
So that's a good question, because I think there's two answers to that, if I may, right? One of which is I have to believe we can get there, right? There's nothing that we can't. The challenge we have at the moment is all the quantum computers operate at incredibly low temperatures. So they operate at 4 Kelvin, which is minus 260 odd degrees C in that. So you need liquid helium to run them. You need microwave waveguides, and you've got a computer that has a few qubits that fits into, you know, something the size of your bedroom, right? Probably. And so I'm not going to carry that around like my phone now, but you know, this is the process of how things go, right? This is how everything starts, and I have to believe that at some point it may be possible. And I think that, to me, is what makes this really exciting, right? Is the possibility that it could get there.
That's sorry, I was muted by mistake.
Yeah.
That is actually interesting. There is another question.
Yeah.
I can visualize and understand the one and zeros of how computers work on and off. Is there a clear representation on quantum computers? How can something be in two states at the same time?
Right. So that's a very good question. So I'll share with you the kind of how I think about this. So basically, if you have a quantum bit or a qubit, it has two states, much like we're talking in the classical, if you like, world, right? It's on or off, right? It's a bit like that switch, right? It's on or off. If I take two qubits, or if I take two classical bits, right? I have one that can be on, one that can be off, okay? And I can control those. The quantum bits, what makes them interesting is I can do that process of entanglement together. So they become one thing. And what entanglement really means is that I can't describe those anymore individually. They're kind of one entity, I think we were saying before. What that means is that you can start doing operations simultaneously on those two qubits of information. And as I understand it now, you can do things like logic gates based on a superposition of those two, rather than doing things individually. And that's why you can get situations where you get huge speed increases in certain things, because you're doing simultaneous operations. Because if you like, you encode the information, you entangle it, and then you do an operation, okay? And you can do that together on many qubits if you can entangle them all together. So maybe coming back to it, it's not that it's in the two states at the same time, it's just that we don't know which state it's in. And so we can't describe whether this one is up and this one's down, because until we do a measurement, we don't know. And I think this goes back to Schrodinger's cat paradox, right? Which I think many people have heard, right? If you have a box and you put a cat inside the box and you seal it up, the cat, we don't know until we open the box whether the cat's alive or dead, okay? And so that's the process where we say there's a superposition of that. It's actually in both states until you open the box and you measure it, and then it's pretty obvious which state the cat is in. Because if it jumps out at you, then it's alive, and if it doesn't, then, you know, sadly it's dead. So I think hopefully that answers the question, at least how I understand it.
I think so. So one thing that I've been hearing, we're talking a lot of qubits. Can you kind of tell our audience what qubits are? I'm trying to think of the best way to kind of, you know, describe that. So usually a qubit is a material which in a physics property can store two states. And so we use things in superconductors with what's called a Josephson junction, where we can put the system in two levels. So we can then probe as to whether the system is in one state or is in another state. And so if you can optically measure it or use
gigahertz electronics, you can measure which state that system is in. It's very difficult to describe in a way what a qubit necessarily is, because you have this physics idea of something that's a two-level system that you can probe, and then physically you have how you make it, which is maybe from a superconductor with some material that's not superconducting in the middle to make a junction, and it's the connection of those two that allows us to be able to make that a qubit.
Yeah, thank you, Stuart.
No
Another
problem.
question in the chat: how could quantum materials break the 9 nanometer, over 10 nanometer limit?
So I think the way that I would perhaps describe that is, it's not that we're trying to break necessarily the limit of patterning, right, that comes from silicon, right, because it's how you can pattern the material to what length scales. What we're actually saying with quantum materials is they have absolutely new properties that allow us to do things that are better or faster. And it's not that we need to pattern things to be necessarily smaller. It's the fact that we can make devices that are either much more efficient or much better, that can do the same operation as silicon, but faster. It's not that we necessarily need to pattern them at a different length scale, right? I think when I come back to saying we have this limit in semiconductors, the way I understand it is that it's the miniaturization of silicon, right, in going from patterning that was big to small, that's meant that we've had this scaling as Moore's law, right, where computers keep going up in speed because you can put more and more and more transistors on a chip, right? What we're doing is saying, let's throw that idea out and start with new materials that give us better properties to start with.
Sorry, I got mute myself. There's another question that I think is a very interesting question. Why does quantum internet requires to be in a superconducting, very cold environment?
So I think, I think for the qubits, one of the things that I can say is that the reason you need to be in a very cold environment is because we need the materials that I was talking about to be superconducting. Now, superconductivity is something where when you pass electrons through a material, there is no resistance. That, unfortunately, is a property that is only displayed in most materials at very low temperatures. And so the materials only become superconducting at very low temperatures. And therefore, if a qubit is based on that technology, we need to cool it down so it becomes a superconductor. And in fact, it turns out that that's research that has been done in other areas, because we would like to be able to do power transmission, right, without losing loss, right? All the power transmission lines that are delivered to houses all have, resistance with them. And in fact, a lot of how electricity is generated is actually goes into just the losses of getting it to your house. And so it's an offshoot of a technology that's used in other areas, or hopefully in other areas, to be able to do that.
Very cool. Another question in the chat, Stuart, for you.
Yeah.
What properties of electrons are used in quantum computer hardware, like spin, plasmons, polarization, magnons? How should it relate to optical properties? Can just all optical properties of material be sufficient for quantum computer hardware?
So I need to think about that for a second. So I think what I would do is I'd say it depends a little bit on what technology you're using for that. Mm-hmm. So I mentioned before these superconducting qubits, right? And they can have technology where they're read out using microwave electronics. And so if you see this picture of IBM's quantum computer, right? It's this big gold, how should I say, big gold type cryostat, right? I'm looking for a better term.
A cryogenics type of thing.
Exactly, and it's got all these microwave waveguides, so that's how we're using it to read out the quantum. There's other technology using different qubits where we're using, lasers and optical ways of doing it. And I'm not an expert on necessarily how all those couple in, although there are different ways of measuring it, because what it comes down to is every material. The fundamental of the qubit is you have these two-level systems where you have two states, and you need a method to probe that, and you can either do that through microwave measurements, optical measurements, or anything else. And so it depends on what type of qubit technology you're using for that.
Mm-hmm. Very good. One other, there are a lot of questions today, so that's very, very good. What is the overall goal of quantum electronics?
I mean, I would say the goal of quantum electronics is to beat what we can do with normal silicon or normal electronics that we have at the moment, right? And I think that, I come back to this, the thing I was saying before, right? A quantum computer, if you like, will do every operation. And in fact, there's a physics law that it will do every operation that can be done on a classical computer. It's the question of time. There's things like factorizing numbers that may take till, thousands of years to do on a classical computer. If you can do it now in minutes in a quantum computer, that's a clear advantage. So
a better iPhone or ever, those.
Exactly. I mean, one of the things that I think I've kind of come to realize is that just because a technology is not necessarily used in an iPhone doesn't mean that it generates the next technology, right? One of the things I find really interesting is that if you just think about computers, we use the next generation computers to design the generation that happens after. So if you think about, I come back to reading somebody like Apple generating a new processor, right? They've used a computer to do that. And so the system accelerates itself every time you use it. So just because you have a quantum computer doesn't necessarily mean it needs to be in an iPhone to be beneficial. It's how we can use that computer to then generate ideas later. If it ends up being able to solve physics problems that give us materials that are being used in those devices, right? That's how we go forward as society, right?
Great. So before I know we have many questions in the chat, and what we're going to pivot a little bit. We're going to pivot to career choices and mentoring and so forth. So if we have some time, we will go back to some of the other questions. If not, I will give them to Stuart. and I will reach out to the folks and get the questions answered to you. But before we go to that, we pivot to that piece. I know there's a lot of students in conversation, and I know that a lot of, we take a lot of coding classes, and traditional coding, it's part of what we learn in school, the Python and C++. So quantum computing will be using this traditional computer coding languages, or really new ways to code will have to be created in order for, for this, for the computers itself to work?
Yeah, I think, there's two areas to that, right? I think even just like, I talked about logic, right? And I go back to when I was in university, right? We did Boolean logic, and we all learned in NOT gates and AND gates and how to do that kind of math that was associated with that, down to now how to program computers through everything from assembly, as you said, up to C++. And in quantum world, right, we need the same type of things, but it's all different, right? So you have how to use quantum gates, there's the languages of quantum computers. And so that's a field at the moment that is very new, but it's certainly one that's very much on active study. And I think that's a really interesting area.
Cool. So Stuart, how did you always knew that you wanted to be a scientist? Like you woke up one morning and said, hey, I'm going to be a scientist today.
That's a good question. So I was always very interested in science and technology. And so in electronics, and in fact, I grew up and my parents were scientists and were chemists. And so I was kind of fortunate in that sense that they always encouraged me, but I was always kind of swithering between whether I was going to do engineering or physics. And so I was always interested in electronics and computing, and you mentioned things like C++, right? So I did a lot of both when I was in high school and computing, high school and university, did a lot of coding, played a lot with computers, and so I was always on that fence. And I think when I was at the end of high school, I really decided that I kind of like doing science. And what I've realized is that what I love about doing physics and science here is that you get to do both. And so in a way, I get to do the physics of what we're talking about and talking about the materials and that, but I also rely on the fact that I spend a lot of time doing coding, and to be able to analyze my data to build the instruments that we actually use at the light source. I use computing. I do engineering. I work with electronic and mechanical engineers to build these big instruments that we use. And so, we have a lot of support at the National Lab, but I've done everything from learning to use a lathe through computing to doing that. And that to me is really exciting because it gets to play with a lot of really cool new technology and at the same time do science. And that to me was kind of what really has attracted and kept me in this field.
That's a very cool balance of, you know, playing with toys and at the same time doing, I didn't want to call it toys, but playing with toys
Yeah.
and doing real science at the same, doing the science that you love at the same time. If there was if there's somebody's interested in getting to the field of quantum science,
Yeah.
what would you recommend the students to study, whether it's computer science or physics, or perhaps just a combination of both?
So I think you can do either. And I think what's important is to do what you really feel you want to do in this field. I think, the reason I say that is I think that the field is big enough that it's going to need everyone from, as I said before, right, people to go and, program quantum computers, through material scientists like myself to understand how the materials operate, through to people that are going to build the technology, that how these devices are going to operate, through the engineers. And so there's a huge suite of there that needs to happen just to kind of keep this field going. And so, I think that we need all, I think we need all disciplines. Yeah, exactly. And I think all disciplines are as important. I liken this back to with NSLS-II, right? It's the people that do all the engineering are as important to the scientists doing the measurements, right? Because it's a team that get together to do the science at the end.
Yeah, science is no longer done by individuals. It's really
Exactly.
it's really a collaborative endeavor, and so it requires many of us to play a role in the big picture of it. What was your path? So how did you get to where you are today? How did you navigate that piece?
So that's interesting. So I grew up in the north of Scotland, so I'm going to talk from there. So in high school, I did physics and chemistry and math, and I went to university and did my undergraduate in physics. And I was kind of, again, fortunate because in the last year that I was an undergraduate there, we actually got to do experiments at a large-scale facility. And what was nice was that we got to actually do, at this time, it was a trip to Grenoble in France to go to the SRF, which is a synchrotron that exists there, like the National Synchrotron Light Source. And so I went from this world where you had an experiment in a lab to suddenly walking into a facility that was 1 kilometer in circumference and had 40 different experiments running on beamlines that were 50 meters long, right? And it really has kind of brought to me, at least, what this large scale science is when you do this. And so at that point, I realized I loved doing that and stayed on and did a PhD at the university doing X-ray scattering measurements. When I finished my PhD, I actually went and did a postdoc in Grenoble in France there for like 3.5 years. And then I left after my postdoc to come here to Long Island to work at Brookhaven Lab.
So how long you have been in Brookhaven since when then?
So I arrived in 2006.
And for folks that may not know, a postdoc, after you finish your PhD, nowadays you have to do additional specialized training in a very specific area that you want to focus in your scientific career. And we call that a postdoc. Length varies, right?
Yes.
From 3 years to forever. Just joking. Almost that way. So and then you came to Brookhaven Lab, and it has stayed here since. Maybe we talked about this a little bit. So your role right now in the center is focused on the material science piece,
right?
Yeah.
So at the center, I do the material science, and then at the synchrotron, so I kind of wear two hats, if you like. So at the materials center, we're doing the material science of these quantum materials, and at the NSLS-II, we have a suite of beamlines which are actually used for doing those measurements, but we also offer those as a user facility to other people to be able to do experiments.
If what kind of preparation would you suggest to a high school student or a college student that is interested in getting into this field as it advances, right? Thinking about forward, what kind of courses you would suggest, what kind of preparation or advice would you give to the high school or college student?
I think what I've relied on the most, I think, it started as a fairly traditional physics role, right? So doing, physics, chemistry, math as being the kind of the role for that. And then I think it's about getting into, a good university program that's going to offer that foundation in physics that we get. or in computer science, right? And I think,
Mhm.
one of the things that's interesting at the moment is I think we're blurring the lines between a lot of these,
Mhm.
right? Computer scientists are now kind of getting close to physicists, and physicists are getting close to computer scientists because they're
Mhm.
using that. So I think it's about looking at the technologies we have at the moment
Correct.
and learning the proficiency in those, right? And that's, you know, what I was saying is the physics, the maths, the computational, the computing that happens.
And doing internships too. I think that's something that I personally, it was a benefit. Did you
Yeah.
do it? Were you able to do internships in Europe, or that's as part of your or your trip or your experience in Grenoble was that internship?
Yeah, so we don't really do the same kind of
Mhm.
internship. And so one of the things I think I really like is that we have that program at the lab, right? Because that's something that wasn't really on offer for
Mhm.
me when I was in either in high school or university. And so I think it was the fact that I did typically in the UK, a degree is 3 years, bachelor's degree. And I was one of the well, first years, right, where they started offering a master's degree as being a 4-year degree, where they put it together. And that this last year was always the possibility to do research.
Mhm.
And so it was that you could call kind of like an internship, right, that started off, understanding about X-ray diffraction and so on.
Yeah, for the folks listening, yeah, the Brookhaven has there is a couple of programs. The high school research program for high school students, and then we have the science undergraduate laboratory internship that's a DOE funded for college students. So
Yeah.
those opportunities are there as well, and there's a value to that. Before I ask you your very last question, there's a questions on the chat. Uh, Still, on the science. So I'm just gonna. Uh, uh, Ask you maybe one or two before because we're getting close to the time, to our ending time. Um, can you see quantum mobile applications on mobile devices in the future?
Um, I think I can. And one of the things I would offer is that what's I think interesting is that you can use how should I describe this? So I think that just because you don't necessarily need the quantum computer in your phone to be using what it does. And the reason that I say that is we've probably all come across things like, well, we know Siri and I think Google have something else, right? What's interesting about that is that the connectivity that we have now through the internet means that you don't need that in your phone. And in fact, when you say, hey Siri, and ask a question,
Mhm.
what's happening is that voice is being recorded, being sent out to a cloud, to a data center that's run by your provider and processed and come back. So I think one of the possibilities that's coming up in the future is that you can actually use the properties of a quantum computer. You don't need it in your phone because you can send the information to somebody who has a quantum data center and actually send the information back as a possibility.
I did not know that. I learned something today. Yeah. And then I will take my last question. What are other uses for quantum electronics besides computers?
So I think one of the things that we're looking at, it depends whether you mean a little bit with the quantum devices, but if I take the quantum materials that we're using, right, they have other applications in things like sensor materials and so on. And so one of the things that we were looking at a while ago was actually looking at quantum materials for being things like magnetic sensors, because we can change resistance properties by orders of magnitude, whereas that normally doesn't happen. And that's not necessarily using a quantum device, but it's by using this going back to this idea of these electrons that are now behaving in a very quantum way, right? We call that strongly correlated. By using that, we can get whether it be sensors or other things with really unique properties, and that's kind of the hope that we can then use those in devices, right, and make better devices.
So Stuart,
Yeah.
any advice that you would give to our students and teachers and educators that are listening? Because that would be, as a last question.
So I think, for me, I just want to say this is a really exciting area, right? I mean, I think that there aren't many times when in your career you kind of see things change in a really positive direction, right? And so, looking at where the avenue of this is going is really exciting. And I think, one of the things I came back to is thinking about how things have changed, even at the time it took us to build NSLS-II, right? I mean, that's taken us 12 years to build the facility, and just how things have changed, right? Computers back then were not as portable, didn't have as much power, right? Your internet connection at home was 3 orders of magnitude slower, right? And these are all things that are really exciting and driven. And now we're opening up the possibilities of quantum computers. You mentioned at the beginning artificial intelligence, right? I mean, this is something that we're starting to use in experiments at the NSLS-II to keep the human out of the loop, because the experiments are happening so fast now that we can't actually have people making decisions because they take too long. And so being able to do more autonomous experiments is kind of really, I think, really cool. And so this is an area that is kind of exploding, as going from experiments to being able to do computing on the side, to be able to feed back to the experiments, to make the experiments faster, to make new materials. And so I really think this is accelerating. So my advice is, I think this is, if you're interested, this is a really exciting field. And I think, people in this audience are really going to be able to see some of the benefits of this, of things that are only being dreamed now, right?
Yeah, the benefits, and perhaps being contributors to those, right?
Right, exactly.
To the science, to the new science that will emerge from it.
I mean, come back and teach me how how to do quantum operations, right? That would be great.
Exactly. Thank you so much, Stuart. It was wonderful today. Folks, this is the time that we have for today. Again, thank you, Stuart. I really appreciate your time. This was wonderful. I learned something. Quantum is a new area. It's a challenging topic to convey to folks. So I think it was wonderful. It was greatly done today. Our next Science Thursday will be October 17, 2020. And our guest will be Dr. Peter Gaida for the NASA Space Radiation Laboratory. And he will be talking to us about the research that the facility does in the understanding of cosmic radiation and the effect in healthy tissue that leads to safer space explorations for astronauts and possible improvement in cancer fighting treatment for all. So again, thank you, everyone. We'd like to thank Brookhaven National Laboratory for hosting this event today, and encourage you to check our programs at www.bnl.gov/education for research and internship opportunities available, and also our available virtual content as well. Thank you so very much. Stay safe. Wear your mask. Thank you, Stuart.